not to mention how and why the star likely evolved. Along the way, I discovered that you and I share some surprising habits with star-nosed moles. The experience with star-nosed moles gave me a taste for unsolved biological mysteries and extreme adaptations. It inspired me to investigate other strange creatures like tentacled snakes, water shrews, electric eels, zombie-making parasitoids, and even humans with some seemingly magical traditions. Electric eels, for example, turned out to be one of the most underestimated creatures on our planet. That's saying a lot, given their legendary status as electricians capable of generating hundreds of volts for both offense and defense. For centuries, it was assumed that an animal with such impressive weaponry had no need for sophisticated behavior. As I soon discovered, electrical power is only half the equation. The other half is, as they say, all in the delivery. The eel's behavior allows it to use electricity to rival weapons from science fiction. I should know. I tested the eel's electrical weapon on my own arm. The eels demonstrate that even animals we have studied for centuries still hold secrets to be uncovered. And there's another more specific lesson. Where you find extreme anatomical traits, you can often expect to find equally extreme behaviors. There's more, of course. If you want to learn about a predator that sets the ultimate trap, as if it can predict the future, or if you need to know the best strategies to avoid becoming a zombie, you'll have to continue on. Each of these cases reveals a masterpiece from evolution's work. But there is more to learn from these animals than simply the details of particular adaptations, as wonderful as they may be. Just as studying one masterpiece in a museum can teach us much about the artist, each of these specific systems can teach us generalities about animal behavior, brain organization, development, and evolution. This is an important and often unappreciated theme in science. To mention just a few examples, much of what we know about how brain cells, neurons, conduct signals was figured out in squid because they have giant nerve fibers which evolved for super-fast escape from predators. The result was a giant leap forward in our understanding of all animal brains, not to mention the Nobel Prize for the scientists. Similarly, the means by which neurons most quickly communicate with one another, the electrical synapse, was discovered by studying the humble crayfish, which uses its fast-conducting neurons to escape predators. But as you'll learn in Chapter 5, it's not always fast enough. On the predator's side, venoms of snakes and snails are a rich source of potential therapeutic agents. Some venoms are already being used to treat chronic pain, and many others are being investigated for potential stroke and cancer therapies. Even a predator as strange as an electric eel has advanced science immensely. First by inspiring Italian scientist Alessandro Volta to invent the battery in 1800, and much later by allowing the isolation of a key molecule, the acetylcholine receptor that is required for virtually all skeletal muscle activity. I could go on. In short, you can't swing a stick without hitting a major scientific advance that resulted from studying diverse and specialized animals. That's true because all animals play by the same evolutionary rules. The result is what Richard Dawkins has so elegantly called the greatest show on Earth. One of my goals is to showcase some great performances from that show. But I have another goal as well. I hope the listener will learn something not only about these incredible animals, but also about the process of discovery. Like everyone else, I'm attracted to mystery.